A caterpillar gets attacked. It has no claws, no teeth, no armor, so it does something that looks completely ridiculous. It bends its body backward, plants its rear end. Then, suddenly, it turns itself into a wheel. The mother of pearl moth caterpillar can use this recoil to launch itself backward, rolling away from danger at roughly 40 times its normal speed of movement. For a fraction of a second, it looks like evolution finally did it. A living animal has become a wheel. Then the caterpillar stops and crawls away. That's the strange part. Animals can roll. Animals can spin. Biology can build rotary machines. But after roughly 4 billion years of evolution, no large animal has ever grown a true wheel. Why? Because the difficult part was never making something round. It's making something round that can keep turning. Imagine attaching a wheel to your leg. Now make it spin continuously. Your leg stays still. The wheel keeps rotating. What happens to everything connecting them? Blood vessels twist, nerves twist, tendons twist. Eventually, something tears. Your body is not built from independent pieces. Everything is connected to something else. And that connection is exactly what a wheel doesn't want. A wheel needs one part to rotate forever, while the other part doesn't move at all. Humans solve this with bearings. Biology has a different solution to rotation. It usually avoids it. Look at your wrist. You can rotate your hand surprisingly far, but the movement has limits. Your bones collide. Ligaments tighten. Tissues reach their mechanical limits. Now imagine asking the joint to keep rotating in the same direction. 1 turn, 2 turns, 10, the problem isn't the joint anymore. It's everything passing through it. A large animal needs blood. It needs nerves. It needs muscles. It needs a constant supply of oxygen and nutrients. So a freely rotating limb would need to disconnect itself from the body's infrastructure. And that creates a bizarre engineering requirement. The wheel has to be attached without actually being connected. But biology has something that comes surprisingly close. It's just much, much smaller. Some bacteria swim using a flagellar motor. The motor sits in the cell membrane and rotates a filament that pushes the bacterium through its environment. It isn't simply a metaphorical wheel. It is a genuine biological rotary machine. And it can rotate hundreds of times per second. Your cells have rotary machinery too. App synthase is a molecular motor that uses rotation to help produce app, the energy currency of cells. Experiments have measured individual app synthase complexes rotating at well over 100 revolutions per second. So biology knows how to build a motor. It knows how to build an axle. It knows how to make one part rotate while another part stays comparatively still. The wheel isn't forbidden. The problem is scale. At the microscopic level, a machine can sit directly inside the chemical environment that powers it. A bacterium doesn't need a kilometer of blood vessels. It doesn't need lungs. It doesn't need a heart. Its entire world is only a few micrometers across. A large animal is different. Your cells are scattered throughout a body that can be meters across. Oxygen has to travel from the outside world to your lungs, then into your blood, then through branching vessels until it reaches individual cells. The same is true for nutrients. And waste. And chemical signals. The larger the animal becomes, the more infrastructure has to connect everything. A wheel wants isolation. A large animal requires connection. Those two requirements don't get along. But let's say evolution somehow solves that. Give the animal a perfect biological bearing. Now we have another problem. The wheel touches the ground. Every second it rolls, something is grinding against it. Sand scratches it, rocks strike it, mud clings to it, hard surfaces wear it down. A living structure can repair itself. A completely detached structure can't. That's why your hair can grow. Your fingernails can grow. Your skin can replace itself. The material you see may be dead, but something alive is constantly producing it underneath. A wheel has no living root, and if you give it one, we're back to the connection problem. Same problem. Different disguise. So even a perfect biological wheel would have to solve 3 separate engineering problems. How does it rotate? How does it stay alive or repair itself? And how does the animal keep it supplied without stopping the rotation? And then comes a problem biology cannot solve inside the animal at all. The ground. A wheel is not a complete locomotion system. It is a partnership between the wheel and the surface beneath it. Put a wheel on a smooth, hard track, and suddenly it becomes extraordinary. Put it on deep sand, and the sand moves instead. Put it in thick mud, and the wheel can dig itself deeper. Put it in a forest, and roots, branches, stones, and uneven ground become obstacles. A leg has an advantage a wheel doesn't. A leg can choose its next contact point. It can step over the obstacle. A wheel has to meet every obstacle continuously. And that matters because Earth spent most of its history without roads. Forests, wetlands, rivers, loose soil, broken rock, steep slopes. There was no perfectly prepared track waiting for the first wheeled animal. But here's a strange twist. Humans eventually proved that the wheel itself wasn't the difficult part. People in pre-Columbian Mesoamerica made wheeled objects and toys. Archaeologists have found ceramic wheeled toys at multiple sites in Mexico, so these cultures clearly understood the basic principle of a rotating wheel. But the wheel did not become the foundation of their transport systems. That tells us something important. Knowing what a wheel is isn't enough. The environment has to make the wheel worth building, and humans had another advantage. We can change the environment. We can clear a path, lay down boards, build roads, smooth surfaces, make bearings, replace damaged parts. An animal gets none of that. It has to evolve for the world that already exists. And that brings us to the real barrier. Evolution can't plan. Imagine an animal developing a small structure that might eventually become part of a wheel. But right now, it does nothing useful. It doesn't make the animal faster. It doesn't help it escape. It doesn't find food. It simply costs energy. Natural selection doesn't care that the structure could become useful 10 million generations later. If it makes the animal worse today, it's a disadvantage. And disadvantages disappear. That's why evolution can build something as complicated as an eye. The first step doesn't have to be an eye. A light-sensitive cell is already useful. It can tell the animal which direction the light is coming from. A slightly better version gives slightly better information. Then another improvement. Then another. Every step can pay for itself. A wheel is different. A partial wheel doesn't behave like a worse wheel. It behaves like something that isn't a wheel. That's the trap. The final invention can be brilliant, while the road leading to it is useless. Humans can cross that gap because we can see the destination before we build it. A mechanic can make a part that does nothing by itself because they already know what it will connect to. An engineer can spend months building a component that has no immediate purpose. Evolution can't make that trade. It doesn't know what the next generation will need. It only preserves what works now. And this changes the way you should think about evolution. It isn't an inventor searching through a toolbox. It is more like a blind filter. Variation produces possibilities. The environment removes the failures. Whatever survives becomes the starting material for the next round. Then the filter runs again, and again, and again. That's how something can become extraordinarily complicated without ever having a plan. It also explains why some inventions are strangely absent from nature. Fire, metalworking, radios, engines, these things don't become useful piece by piece in the way an eye can. Their parts become valuable when they are assembled into a working system. A spark isn't a fire. A lump of ore isn't a steel machine. A radio component sitting alone isn't communication. Humans can assemble the useless pieces because we know what they're for. Evolution doesn't. And that's why the missing wheel is more interesting than the wheel itself. It isn't evidence that nature failed to discover an obvious invention. It's evidence that nature was never trying to invent anything. It was filtering possibilities, one generation at a time. And yet that blind process produced creatures that can fly, see, hear, generate electricity, and build molecular motors that spin hundreds of times every second. It even produced a brain capable of asking, why doesn't nature have wheels? That's the real irony. We think the wheel is obvious because we already know the answer. But obvious inventions are often obvious only after someone has shown you the path. Nature never got to look at the finished machine. It had to survive every step before the machine existed. And that gives us a strange prediction. If life exists somewhere else in the universe, it could be completely unfamiliar. It might have different chemistry, different senses, different bodies, different ways of moving. But if evolution shaped it through the same basic rules, it will face the same problem. A final structure can be extraordinarily useful, while the steps needed to reach it may be useless. So maybe alien life won't move like anything on Earth. Maybe it will swim through oceans beneath an ice-covered world. Maybe it will crawl through an atmosphere denser than ours. Maybe it will move with limbs, membranes, cilia, or something we haven't imagined. But if one of those creatures ever rolls, the important question won't be why it has a wheel. It will be how evolution managed to build everything around the wheel without needing to know the wheel was coming. And somewhere on Earth, the caterpillar already gives us a tiny preview. For one brief moment, it becomes a wheel. Then the trick ends. The body unfolds. The legs touch the ground. And it goes back to being a caterpillar. Maybe that's the closest evolution ever needed to get. Not because the wheel was impossible, but because evolution had a billion different ways to move, and almost all of them worked without one. The caterpillar rolls when rolling saves its life. Then it stands up and walks.